Hello mathematicians, I'm going to go through some transformations of trigonometric graphs, also relevant to transformations in general for the mainly aimed at the IBAA course. So first we need to have, and I'm presenting this video as revision, okay? So I'm not going to go through precisely why all these things work, but we take a fairly formulaic approach in IB, and you really do just have to remember these definitions. Now I'll talk through, in fact I'm going to show you these on the CAS calculator, so make a note of these or at the very least screenshot it so you can refer to it. You might have noticed the language I was using there. So we're going to start with dilations, and first I'm going to do a dilation of my function. So I go tab. So we've said this is going to be a dilation from the y-axis by a factor of a half. Now let's just analyze what's happened there. All the distances from each point to the y-axis, this axis here, have been cut in half. So this point here, whatever that distance was, about, I don't know, 7, that is now here, 3.5. This distance here has been halved to go here. Draw a little arrow there to show you what's going on. This distance here has been halved. And it's always the distance from the axis. So this point here hasn't moved at all. So that's why I refer to it, even though it's a horizontal dilation, we refer to it as from the y-axis. Don't just say horizontal dilation. If we change it and make it put the 2 on the outside of the function, we can see we end up with a dilation from the x-axis. It's a vertical dilation where we have doubled all the points, going from double the distances. So this distance here we can see is 2, that is now 4. This distance here was 0 for this point, so that hasn't moved. This point hasn't moved. This point was 1 below, and it's now 2 below. Now there's a bit of a pattern here. You'll notice that this was f of 2x, and it multiplied the distances by a half. This is 2f of x, which doubled everything. Now I think it's fairly intuitive to say that multiplying is going to be a stretch. If not, you're just going to have to remember it. And the other little helpful way of remembering is that anything that happens inside the function moves the function in a horizontal direction, but in the opposite way you expect. So anything inside the function affects x, but not in the way you expect. And the way to remember this is that you never trust your x. We don't go into the nuts and bolts of the mechanics for like why that works. For AA, we are just going to take it as read. And this idea of not trusting your x works for, well, actually, it doesn't quite work so well for reflections, because if we put a negative here, we can see we have reflected in the x-axis. So the negative was on the outside. Just show you again. The negative is on the outside of the function, which means it's a vertical change, but we say it's in the x-axis because that's how we describe that vertical change. If we put the minus inside, it's a reflection in the y-axis. It's a horizontal reflection. Now, the whole not trusting your x doesn't really work here because there's only one way you can reflect something. But it does work when we consider translation. So if I go x plus 2 feels like things should move to the right, but in fact they move to the left. And if I go f of x and we stick the plus 2 on the outside of the function, the whole thing goes up. So when the plus 2 is on the outside of the function, it affects the y's, and it affects the y as you would expect. The other thing we need to consider is how do we combine these transformations? So let's say I went a f of, not x, b x plus c plus d, f of, that's a g of x, this one. So we can see we have a dilation times by a, it's vertical, from the x-axis. This gives us a dilation times by 1 over b from the y-axis. Then we have a translation C to the left, and a translation D up. Now it's very important that if we're going to have things in this order, we would have our dilations. Reflections, they actually go with dilations because mathematically they're kind of the same. You're multiplying by a negative, but we would separate it. And if A or B were negative, we'd have to say, oh, that's also a reflection in the x-axis or reflection in the y-axis. And then we have translation. Now this order only works if we have this part here factorized. So we must have a single x coefficient. And I'll show you what I mean here. We'll go back to our graph where we have plotted f of 2x, so that's a dilation by half from the y-axis. If I go 2x plus 2, intuitively that feels like it should move. We know plus 2 moves to the left. Feels like it should move by 2, but in fact it only moves 1. And the reason for that is it's the same as 2 bracket x plus 1. Now again, we're not going into the mechanics of why that's the case. We just need to know that it is in fact the case. If we're going to do these transformations and we're going to combine them so that dilations and then reflections and then translations are in that order, we must factorize the x coefficient. So now we apply this to some questions. Now, there's a very common thing for periodic, for trig functions, where we would say for sine, it works for sine, cos, or kind of for tan. If we have sine of bx, we would say the period is 2 pi over b, or we would say b equals 2 pi over the period, depending on what we're trying to find. That is the same for sine and cos. For tan bx, it's kind of the same, but because the original period of tan is pi, it's going to be pi over b. So when we're asked to write down the period of g, we can think about it in one of two ways. We could either say, well, we know the period is 2 pi over b. b is 2, so 2 pi over 2, which is pi. Or we could say, well, the 2x here means it's a dilation by a factor of a half from the y-axis. So basically our curve, our original sine did this, it's been squished, so it's doing that now. So we can see the period has been halved. Either way, the period is pi. When we sketch the curve, we also need to know what the 3 does. The 3 is a dilation from the x-axis. So the minimum and maximum of sine is usually -1 to 1. That dilation of, we can just draw this. It's like scrappy drawings, but whatever. Sine is usually -1 to 1. If we stretch it, let's go -3 to 3. It does something like this. And we know the period here is pi, so that is everything we need to sketch it. I like to plot some points. So we know it's going to go up, down, down, up, down, down, up, and then same thing over there, making sure we plot it for the required domain. Things to note, we should have a changing concavity, so this bit here isn't particularly good. We probably want to make that a little bit rounder. Some people try and get this vertical, and the gradient is not undefined there, so it's not trying to go down the axis like that. It's pretty much as it looks there. And we've made it go through these key points, the maximums, the minimums, and the axial intercepts. Finally, for C, write down the number of solutions. Well, we can imagine drawing a line across here. That's what it's asking us to do. And we can see there are 1, 2, 3, 4 solutions. Let's say this is a fairly easy-ish question for transformations. Let's try another one. In fact, you should be able to pause the video and try this yourselves. It's working in pretty much the same way, except we're given the graph and we have to work out the values. So the value of P, we've gone from 30 down to negative 30 instead of 1 to negative 1. We can see there's been no vertical translation. So we can see P is just times by 30. Another way of looking at that, by the way, we often talk about the amplitude of being 30. So the amplitude is half of that range, if you like. We'd say that's 30 because of that vertical dilation, or the dilation from the x-axis. To calculate the value of Q, we can say Q equals 2 pi over the period, which is pi over 2, times the top and the bottom of the fraction by 2. To get rid of the pi over 2, we have 2 pi over pi, which is 2. These are old questions, and you always see the marks seem very, very high, so don't worry too much about that. Okay, this one has some other stuff going on. Again, pause it and try it. You might well be able to figure it out. In this case, we can see there has been, we can see both from the graph here and from the function and from the graph, it's been dilated and then translated up. We know from dot to t that it's been dilated first and then moved up. I'm going to label these points, so pi, -1 and 0, 3. So we can see then that this entire range is 3 minus minus 1, which is 4, which tells us that the amplitude is 2. So straight away we can see that Q equals 2. For P is always going to be, the translation upwards is going to be to do with this axis, the principal axis, or the mid line, if you like, of the graph. And we can do that by finding the midpoint, or the mid value of 3 and -1. So 3 plus minus 1 divided by 2 is 1. And I think actually the numbers make that fairly clear. -1 to 3, you can probably see the midpoint is 1. Okay, good question. Still on the easy-ish side at the moment. There is a bit more going on here. So I am inclined here to, I was going to label these values just because it makes things easier to see. So we have 329. I should have said, make sure you pause and read the question. I'm not going to stop talking while you do that. So just pause, make sure you read the question. Read it 3 times because there's often something that you'll miss. So we can see the midpoint, the mid-axis is going to be 15 plus 29 divided by 2. So that's 39, 44 divided by 2, which is 22. I'm actually approaching this without necessarily looking straight at the questions. We can see we've got a value there of 22. From there we can see that the amplitude, 22 to 29, is 7. So that tells us the value of A is 7. Now for part 2, we've got to show that, I might do this over here, show that B equals pi on 6. Or to find that, we need to find the period. And we've got to really show this information. So the period is going to be double the gap, this distance here. So the distance between the maximum and the minimum, which is 9 minus 3, we can imagine that this graph continues up this way. And so the whole period is going to be from here to here. So that is the period. We only have half of the period. Okay, just drawn that to show you what's going on. But this line of work on the right is all you would need to write to guarantee that you get those marks. I think 15. Sorry, it's not all you need to write. So the period is 12, and then we would say that B equals 2 pi over 12, which equals pi over 6. So we've shown that pretty comprehensively there. Find the value of D. Well, D refers to the vertical translation, which you can see how we found that before. We can see D equals 22. And finally, write down a value for C. Well, cos usually does this. Okay. Now we know that it's been dilated, and so maybe it was dilated by pi on 6. So the period is now a little bit wider. So I might do this in another color. So the period is now, so after it's dilated by pi on 6, maybe it's doing this thing here. But the nice thing is, if we look at that point, the dilation doesn't affect that. So we can see that the graph has been translated 3 to the right, which means our value for C is going to be 3, because we want the graph, and we've got to be careful when they put a negative in here, we want the graph to be cos blah 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 t minus 3, which, because the negative is already there, we want it to be plus 3. Remember, overall it's minus 3 because it's shifted to the right, and you would expect it to shift to the left if it was minus 3, but we never trust our x. Now notice, as an incidental bonus question, it says write down a value for C. Is that the only possible value? Well, no, not necessarily. It could be that the graph was shifted 3 to the right and then another 12, like another whole period. So it could also be 15. Or we could have shifted it another period and we would have had 27. Okay, that's imagining that this graph, well, as the graph does, goes on and on forever. So in every direction. Right, not that one. So let's get rid of some of this extra stuff. Yeah, that doesn't particularly help either. It could also have been -9. So it could be that the graph had been shifted to the left by 9, because that would be the same as shifting it to the right by 3, because the period altogether would be work for a period of 12. Okay. And this final question, I've deliberately, this isn't an IB question, it's kind of based on something I've seen, because it shows what happens if the Dr. T thing breaks down. So, have a quick read, pause it, have a go. I'm going to draw our graph a little bit. So we've got a maximum at 2, 6, let's go there, and a minimum immediately afterwards at 4, -2. So our cos graph is doing something like this. There we go. So as in the last questions, we need to determine our transformations. We can say that and I find it easier to find the principal axis first, to say, well, 6 plus -2 over 2, so that's 6 minus 4, which is 2, divided by 2 is 2. So we know that our midline here is going to be 2. So that means that the graph, after everything else, will have been translated 2 units up. From here then we can see that the amplitude is 4. So we can see there's dilation times by 4 from the x-axis. We can then talk about the period. We can say that b equals 2 pi divided by the period. Now these points here are 2 apart, means the period is 4. So b is going to be pi divided by 2. So that means altogether the new graph is 4 times cos of pi on 2. We can also know that it's been translated x minus 2, 2 units to the left, very similar to the last question, so won't go into that, plus 2. That plus 2 is this 2 moving upwards here. Okay, I've put this graph in here so we can demonstrate what happens if we try and do things in the non-Dr. T order. So we're just going to consider dilating this graph factor of 2 from the y-axis. So that means that this point here, which we said was at 2, 6, is now going to be over here. It's going to be at 4, 6, and this graph is going to start in the same spot and it's going to come up like that and then down. Now, if we apply this approach naively, we would say it's 4 cos factor of 2 means we are making this dividing by 2, so it's going to be pi divided by 4. If we leave everything else the same though, we can see that it doesn't work because this now reads as a dilation of pi on 4, which is like the two dilations put together, but a translation only of 2 to the right. And it's not 2 to the right, it's 4 to the right. Now you might be able to sort of intuitively work that out, why it would be double, but I think that's a bit risky. So, and I want, it could get even slightly more complicated. So what we can say is, this is my sort of rigorous way of dealing with this. We're going to say let f of x, let our original function be this thing here, be 4 cos pi on 2 x minus 2 plus 2. And we're going to consider g of x to be the new one. So that's going to be g. Factor of 2 means it's going to be a half, then brackets, x plus. Now we're going to include the 2 units to the left. So that's going to be plus 2, and then 1 unit down. Just going to get rid of all that stuff there. And now what we're doing is finding g of, oh, I've missed something out, haven't I? It should be g of x is, bother, should be f there. Yes. So this is a bit like a compound function, a g on f of something, or rather it's, we're going to substitute this part here into x. So g of x now equals 4 cos pi on 2. This is still the same as this bit here. And then instead of x minus 2, I might put this in blue to show you how it's fitting in. What option? So I'm replacing the x here with a half x plus 2. Let's go back to red. Brackets right, and then that's going to be minus 2. And then we have plus 2 on the outside, and then minus 1. So that plus 2 was the thing here, minus 1 is there. So now we just have to expand the bracket. So we'd have 4 cos of pi on 2, a half x plus 1 minus 2 is minus 1. Plus 2 minus 1 is going to be plus 1, which gives us, if we expand that, 4 cos of pi on 4 x minus pi on 2 plus 1. That's one way of writing it. That is a correct equation, I think. We could also factorize out the half from inside and say it's going to be pi on 4, because we've taken out the half, x minus 2 plus 1. That now tells us what our final curve is in relation to the cos graph. And I just thought it'd be worth looking at this so we can see how it does indeed work out. So we had our maximum point here, 2, 6. That would have been dilated by a factor of 2 from the y-axis, so it would have gone over here to be 4, 6. Translated 2 to the left, it would be back to 2, 6, and 1 unit down, and it would indeed put us there on 2, 5. And we might also just consider this minimum value here, which, I mean, we can kind of see from the graph is going to be 0, minus 1. Oh, minus 2. The dilation of the factor of 2 wouldn't matter because it's on the y-axis already. Then it's going to go 2 to the left, which is going to be about, so that distance there, that distance again, is going to put us there, 1 unit down, and we can kind of see that that has all worked out. Let's say that question is about as hard as I think it could get, but be prepared for it if you're looking at getting those very top marks.